In this last module, we're going to look at the Gibbs free energy and determining, finally, is this reaction spontaneous or not, and why is this reaction spontaneous or not. So at the start of this module, we calculated the change in entropy for the oxidation of ethanol in the presence of oxygen to produce acetic acid and water. And we made a guess before even doing the calculation that based on the changes in phase that were occurring during the reaction, that this reaction would result in a decrease in entropy. But at the same time, we were kind of perplexed by the idea that for a reaction to be spontaneous, we need to have an increase in entropy. Well, we need to have an increase in entropy for the universe. And so that involves the heat component as well for this reaction. So we started off, we calculated the change in entropy to see that yes, we did have a decrease in entropy, which goes against our understanding of a spontaneous reaction, but then we introduced Gibbs free energy and looking at the heat component of a reaction, the enthalpy of a reaction. So now let's take a look at how to calculate the enthalpy of this reaction and then put both the enthalpy and the entropy together to determine the Gibbs free energy and is this reaction spontaneous or not. We can calculate the enthalpy of the reaction the same way we can calculate the entropy of the reaction. We simply want to know the change in enthalpy of the reaction. That equals the summation of the enthalpy of the products minus the summation of the enthalpy of the reactants. Remembering that we have to take into account how many moles of each of those that we have. So for this reaction, right, I can look up the enthalpies of formation of all my reactants and products and simply plug those into my calculation to determine what's my change in enthalpy for this reaction. So to set up this calculation, my change in enthalpy for this reaction will equal the summation of the enthalpy of my products. So I have 1 mole of acetic acid at negative 484.5 kJ per mole, plus the enthalpy from my water. I've got 1 mole of water that comes in at negative 285.8 kJ per mole, minus the summation of the enthalpy of my reactants. The enthalpy of formation of oxygen is 0, so I don't need to include that in my calculation, but the enthalpy of formation of ethanol is 1 mole of that comes with negative 277.7 kilojoules per mole. And again, I calculate this and multiply by moles. Moles will cancel out, leaving me with units of energy. So the delta H equals the summation of negative 484.5 kilojoules plus 285.8 kilojoules minus the enthalpy of ethanol, which is 277.7 kilojoules. And again, remember I said the biggest mistakes that people will make in these calculations are simple addition and subtraction. So we are subtracting a negative number, so really we are adding that 277 to the total. So the delta H for this reaction ends up being approximately negative 492.6 kilojoules. That is a large delta H. That is a large negative delta H, which means this is an exothermic reaction. Exothermic reactions release heat to the surroundings. Now that we have our delta H and we have delta S, now I can calculate the Gibbs free energy for this reaction to determine, ultimately, is this reaction spontaneous or not. So given the values of delta H and delta S for this reaction, what is the free energy for this reaction, the oxidation of ethanol in the presence of oxygen to produce acetic acid and water? We're going to be using delta G equals delta H minus T delta S, and before we get started, we might notice, hopefully we notice, the units of energy are a little bit different. So let's convert units of energy so that they're both in the same format. My entropy, and we'll convert entropy from joules into kilojoules. My entropy is negative 136 joules per Kelvin, and I know that in 1,000 joules I have 1 kilojoule. So I really have 0.136 kilojoules per Kelvin is my entropy. Now I can set up my calculation where delta G equals my delta H. My delta H is negative 492.6 kilojoules minus T delta S. Temperature always needs to be in Kelvin, so I know that Kelvin equals 273 plus my degrees Celsius. So my Kelvin temperature equals 273 plus 25. My temperature in Kelvin equals 298 K. Plug that in, so 298 Kelvin times my entropy, negative 0.136 kJ per Kelvin. And when I multiply, right, my units of temperature cancel out. I had Kelvin here. And subtract, I get a delta G for this reaction equal to negative 453 kilojoules. So yes, this is a spontaneous reaction. Even though I have a negative entropy, I have a decrease in entropy, that's offset by the large exothermic nature of this reaction. So locally, I have a decrease in entropy, but because the reaction gives off so much heat to the surroundings being the universe, I'm going to increase the temperature of the surroundings, and that increases the entropy of the universe. The reaction is spontaneous. So to recap that information, right, the delta G is negative, right? Reaction is spontaneous. So even though we have a decrease in entropy, the reaction releases enough heat to be spontaneous. And that's the important thing that we're looking at here, that even though we have a local decrease in entropy, the reaction gives off enough heat that it warms up the surroundings, increasing the kinetic energy of the surroundings, increasing the entropy of the surroundings, and therefore that makes this process spontaneous because we fulfilled our duty to increasing the entropy of the universe. Much like we can calculate delta H and delta S using the summation calculation, we can do the same thing with our free energy. We can look up the standard free energies of our reactants and our products to calculate the change in free energy for the reaction much the same way, where our delta G would equal the summation of how many moles of products do I have times the delta G of those products minus the summation of how many moles of reactants do I have and the delta G of those reactants. So if we have delta H, delta S values, we can calculate delta G. If we don't have delta H or delta S values, we can calculate delta G by using this summation calculation and the free energies of formation of all the starting materials and products in a given reaction. So that calculation would look much like the calculations we've done previously. My delta G equals the summation of how many moles times the delta G of my products minus the summation of how many moles and the delta G of my reactants. So plugging all that information together, my delta G for this reaction would look like, well, I have 1 mole of acetic acid at negative 389.9 kilojoules per mole, plus 1 mole of water at minus 237.1 kilojoules per mole. subtract the free energies of my reactants, and I have 1 mole of water, and that is negative 174.9 kilojoules per mole. So I'm going to multiply through by moles, right? Moles cancel out, and that's good because I'm looking for units of energy in kilojoules. So I multiply everything by the moles cancel. Now I'm left with the summation of negative 389.9 kilojoules plus the negative 237.1 kilojoules minus a negative 174.9 kilojoules. So I'll add these two together, and then I'm going to subtract the negative value, right, which is the same as adding 174.9 to that. Again, always keep track of your signs and pay attention to your signs, because the most commonly observed mistake I see is addition or subtraction. So adding those two together, I come up with about negative 452 kilojoules for this reaction, right? Much like we saw in the previous slide when I calculated the delta G using the Gibbs free energy equation, right? This reaction is spontaneous. Right, no surprise, this lines up with the other calculation we did. So whether I look at the enthalpy and entropy of a reaction or just the free energy of that reaction and calculate that, both of those ways, right, I should come to the same answer, because again, this is a state function. It doesn't matter how I'm going about it. It just matters where we started and where we ended this process. So what does this mean for you? What does this free energy mean for you in terms of what we do with this free energy? Why does it matter to know what the free energy of something is? We use that free energy as the amount of work we can get done with that reaction. So for example, we want to think about the free energy of something, right? Gasoline has a very high amount of stored energy. That combustion reaction, right, releases a lot of free energy, and what do we do with that? We use that energy to power our car, to move our car down the road. So we can think of the free energy as telling us how much work we can do with that reaction. And that's for spontaneous reactions, right, where we're moving downhill. This is spontaneous. We're releasing free energy. Let's take that free energy and put it to work by moving our car down the road, or moving our car, right, up a hill. So we can take that energy released from a spontaneous process and use that to get work done. Right, so on the other end of the spectrum, if we had a positive free energy, that is a non-spontaneous process, right, because that would be us pushing that boulder uphill. That does not happen unless we put work in it. So if we had a reaction with a positive delta G, that is not spontaneous, but what we can do is pair spontaneous reactions with non-spontaneous reactions. We can take the free energy released from a spontaneous reaction and put that energy into a non-spontaneous reaction, pushing that boulder back up the hill. So we can take that work released from a spontaneous reaction, harness that, and put that to use in getting something done that is non-spontaneous, right? Something that we have to put work into. And so here's an example of that for you. So nature is wonderful at minimizing energy. We do not want to waste energy. So it does a great job of maximizing the energy that we have and using that in the most efficient way possible. And so let's take a look at that. Here is glucose, right? Everybody loves a good sugar. We love sugar because it's a high source of energy. We oxidize sugar into carbon dioxide and water, and in the process of that oxidation, we release a lot of energy. We release about 2,800 kilojoules of energy. So this is spontaneous, right? We can spontaneously oxidize glucose into carbon dioxide and water, and we release a lot of free energy. So what does your body do with that free energy? Well, that free energy that's released from this spontaneous oxidation, we take that and phosphorylate ADP, adenosine diphosphate, to make ATP, and that comes at an expense of about 30 kilojoules. So we take the energy that's released from the oxidation of glucose and we put that into phosphorylating ADP into ATP. ATP, adenosine triphosphate, that's the high energy molecule. That's our energy currency of the cell, right? That's our stored energy. We take that stored energy and now we can carry that throughout the cell and go and phosphorylate other components, other proteins, initiate other processes in the cell because ATP will react. It'll react to lose that phosphate, and in the process, right, this is a state function, so it just matters where we started and where we ended. So when ATP gets hydrolyzed and loses a phosphate and forms ADP, it will release 30 kilojoules of energy, right? That phosphorylation, and so we can go through that cycle over and over and over again using the energy released from the oxidation of glucose to make ATP. ATP is able to travel throughout the cell, releasing that stored energy, right, in the form of being hydrolyzed, that final phosphate being hydrolyzed. So what does your body do with that high energy ATP? And so here's our ATP. ATP is adenosine triphosphate, and so here are the 3 phosphates on ATP. That's our full battery. That's our high energy molecule in the cell. We can hydrolyze that phosphate, and that will come with approximately 30 kilojoules of energy, right, when we break this phosphate bond right here and release a free phosphate. So that reaction is spontaneous. It's got a negative delta G to the tune of negative 30 kilojoules. So how does your body use this energy? Well, let's look at another reaction that your body needs to get done. So the reaction between phosphate and glucose is the first step in glycolysis. The phosphorylation of glucose with phosphate to form glucose 6-phosphate. We need this reaction to get done, right, for glycolysis to occur. The only problem is this reaction comes at an expense of approximately 13.6 kilojoules of energy. So that reaction is not spontaneous as written, but it's a reaction that we need to have take place. So what your body does is it pairs a favorable reaction with an unfavorable reaction. So a favorable reaction is ATP being hydrolyzed to ADP. That has a negative free energy. So if we put those two reactions together, right, what happens to this reaction? Well, now essentially instead of having phosphate plus glucose, my phosphate cancels out of the reaction and I'm left with ATP plus glucose yields glucose 6-phosphate and ADP, and more importantly, I can add these free energies together, and now the free energy of this reaction is negative 16.4 kilojoules. This has become a spontaneous reaction. So I took something that was non-spontaneous, paired it with a reaction that was spontaneous to now get the reaction to occur and occur in a way that is spontaneous, right? I needed this reaction to occur. This is what your body is amazing at, pairing reactions that are spontaneous with reactions that are non-spontaneous in an effort to take the free energy that's released from this hydrolysis of ATP into ADP and use that to get work done. Use that to get reactions done that we need to have take place, right, in order for us to survive. And so here's an example of that. And here's the last biology that I'll talk about for a bit for everyone this was too much biology to see in a chemistry class. So the important things from today's lecture, right? We should know when entropy increases. If you increase volume, entropy increases with an increase in temperature. Entropy increases with moles, and it increases with a phase change as I go from solid liquid to a gas. We've also talked about the second and third law of thermodynamics. So the second law is that entropy is always increasing in the universe for a spontaneous process. The third law, entropy is zero at absolute zero. And the last thing we did was look at Gibbs free energy and use that to determine the direction a reaction will take place, as well as putting that free energy to work. What can we get done with that free energy? So on Monday, we're going to finish off Chapter 17. We're going to look a little bit more at Gibbs free energy and some of the calculations involved with Gibbs free energy and how to determine under what conditions the temperature, the entropy, or the enthalpy would we have a spontaneous or non-spontaneous reaction.